Hi, dear students. After the break, now the time is on one more time CAT application part. The chapter of this week is about structural elements and structures. Remember, under this title, before the break, talk about what is structural element, standard structural element, how we can construct structures, okay, and what is the thing to do in Inventor for having the model of a structural element. Well, after finishing the presentation, my delivery on the chapter content, then to the end of the meeting, remember, I said that okay, this is the thing to do for having the model of a structural element, structural member. I'm going to activate the same project and then make a highlighting on a certain difficulty. And then in the content of this asynchronous meeting, I'm going to inform you on the shooting method. Difficulty, what is difficulty and what is shooting method. Okay, first activate the project. Well, I open Inventor. Default option is the selected option and there is no file. This means there is no active project. So I can activate the already created one. Say this week I said that okay, it is a new project, new studying. After finishing my delivery on the structural elements and structures, I created a project folder and then defined the work as a project, saying structure, etc. Well, today, say after the break, continuing on the rest. The rest again is on CAD part, computer-aided drafting design part. It is to be studied in Inventor environment. Yes, I'm going to inform you on the facility of the software. It is for creating the models of structures. But first, let me activate the project. You know the procedure, how. After being sure that there is no active project, then click on along the Get Started ribbon, of course, Projects button. And then in the dialog box, clicking on Browse tab, show the address of the project definition file. I remember I created the project folder in which address, partition D, Mac114 folder, yes, this folder, this folder, this folder, and yes, that is the list of the existing project folders. One of them is, you see, using the keyword structures. I am sure this is the project folder. Open the project folder, double clicking, and then select the project definition file with a click and say open. That is the procedure, to activate an already defined project. And then clicked on done. Yes. And then to call your memory, on the last part of the session, at which after finishing the presentation, my delivery about structures and structural elements, then remember in assembly environment, yes, I demonstrated how the model of a structural element, it is a standard structural element, can be gathered. It is just via invoking, you know the answer of that question, via invoking it from the library. And then after bringing the model of the element from the library of Inventor, clicking on this listing arrow and from the list selecting content center option. I don't want to say the same things. Then say if you forgot a detail and say still there is a question, then you can find the video record and then have a look at the last part of that video film. Oh, there you can see how the model of a structural element can be invoked from the library to the assembly environment. Okay, and then remember in this scenario saying that this member is to be edited. Well, this end of the member is to be in inclined form, and I said that such a hole, standard hole, is needed. And then thereafter I said that, yeah, well, if you make such a modification, hole drilling or cutting, then this means although the cross section of the member is still the same, have a look at the profile cross section, I in shape, like letter I, it is still standard. The cross section is in the same shape. But since we modified the element, it is not, it is in original form. It has an inclined end and there are some other features. Obvious that for such a modified standard object, can thereafter say that it is not standard. Cross section is standard, but it is not straight member. It has some features to inform the reader on their characteristics. So need to create and provide the detailed drawing for such an element. And then, well, lastly, demonstrated one more time how the views are created. Well, in the example, remember the member, length of the member was 3000 millimeters. I said that in the scenario paper is A3 size paper. So how the projections of such an element can be fit over in the working area, drawing area of the paper under a suitable scale factor. Call the memory. What is the scale factor? Indicate this view, right click the mouse and say edit view. And then I see that the scale which I selected to create the views is 1 to 2. Okay, to be able to fit the images onto the working area, I use a breaking technique. Omitted the projection of the intermediate part. I show I had the image of the terminal portions only. One more time, call the memory on the usage of break lines. Okay, one of the usage of break lines. They are used for a shortened images to highlight that, well, the object has an intermediate portion, but its projection has been omitted. These wave lines just have such a meaning. And then, well, I said one more thing. It is really important. On the profile view, I said no need to show the dimensions. Okay, because the profile, the cross section of the member is standard. Okay, this lateral side view, yes, show the necessary dimensions, because say for instance this inclined surface, reader should know the inclination angle. For this hole, reader should know the location dimensions. Okay, and also, yeah, yes, I forgot to show the dimension, okay, of this hole. Say that indicated with a leader line. Okay, because say, okay, then you can show the diameter. It is of course possible, or with a leader line write the standard specification note for the bolt. Say that the hole is for such a bolt or such a cap screw. Okay, it is also necessary. I'm going to show the diameter rather than writing such a technical note. And of course, precision is to be 0. I know the geometrical tolerance zone size tolerance zone, size tolerance class letter, geometrical tolerance class letter. So for size dimensions, I am sure precision is 0 and the nominal values are to be shown to their integer parts. But here, to inform the reader on all of the things about it is geometry at the cross section, this specification note is valuable. Instead of showing the dimensions on this profile view, what is the radius of this round, what is the radius of this, say, fillet, what is the height, what is the depth, etc., just write this standard designation note. ISO 657 part 15 is the code of the document. It is about this type of structural elements, and SP is the standard code. It corresponds to this I-shaped profile, and 160 is the height of the member at its cross section. Yes, this specification note is sufficient on the technical drawing. Okay, it was at the CAD application part. After finishing the lecture part, then talk about such things. In general speaking, say how the model of a structural element can be invoked. Yes. But here, well, the content of this meeting, the thing to say is that, for instance, you have a truss as the structure. To deal with it is design, to design it, to create it as model thereafter, and the necessary technical drawings. Okay, it's an assembly, of course. Well, here, as the difficulty, I want to draw the attention. Well, think about it. You need to create the model of such a structure. Okay, and then think about at this joint, okay, this member to its inclination, it is end to be finished with an inclined surface. Okay, calculate its inclination angle. It's a trigonometry problem. Okay, knowing the inclination angle of this member, inclination angle of the other members. Yes, you see here, take a pointer or a pen. What I mean this part. This end of this member is to be in the correct inclination, and that angle is to be determined with respect to the orientation of this member as well. And also the inclination angle of this element is important. Knowing the inclination angle of this member, knowing the inclination angle of that member, here you see it is in this example 30 degrees. Okay, calculate the inclination angle of this one using basic trigonometry, and then be able to determine the inclination angle for this inclined end. And then, as I demonstrated last class meeting at the CAD application part, while knowing the inclination angle of the edge, cut the material and have such a finishing surface. Up to this part, well, it is a time-consuming thing, but not a difficult thing. But the difficulty is at the mating stage. Say that imagine you had the model of this member, you have the model of this one, and then be able to position all the members, okay, with respect to each other, okay, to have the joint over there with the necessary inclination angles with respect to each other. Believe me, it is a challenge, not so easy thing. Using the mating facility, okay, if you do not believe me that it is difficult, at home, try. Create the models of the elements, have the models of the elements, just the basic, to its basic shape. Well, just invoke it from the library. And then edit the terminal parts. And then, well, be able to have the models of the members as correctly oriented and mated with respect to each other at not only this joint, but also at this joint. And this member at this joint should be mated with respect to this and that. And also this is to be positioned with respect to the other member. Okay, face-to-face contact, parallel positioning, inclined positioning. It is not so easy and really time-consuming thing and very affordable. So Inventor, the designers of Autodesk Inventor, considering the difficulties, okay, in creating the models of structures, especially at the mating stage, well, for few years it is available. Design, created a design wizard, writing the codes, of course, at the background. And today we have for a few years a push button, almost not a single button, but there are some buttons, group of buttons, I may say. Well, using the facility, it is a design facility. Well, we can solve the positioning problem, mating problem. Because instead of positioning the members one by one, manually with respect to each other using the classical mating tool. Yes. What is the mating tool? Assembly ribbon, constraint button. Clicked on this and then face-to-face contact, parallel positioning or inclined with an inclination angle, position one member with respect to other. Well, if you attempt to use this facility, constraining facility, and then try to mate the components with respect to each other, well, even for 1, 2, 3, 4 cells, such a structure having few cells, it is sure that going to be really a time-consuming thing. And even if your ability is not so good on mating the components, you may completely vanish. So, well, studying on the exercise, I'm going to demonstrate how up to a certain level and then say that the rest is your home assignment. You can see the value of that design facility, really. Well, in my demonstration, I'm going to, create the model of a truss. It is going to be, variant type truss. Okay, something like this. Yes, in this photograph, you see how many cells in this example. Well, saying cell, what I mean, group of members. Okay, for instance, this member, this member, this member, this member. Yes, and diagonally directed one more member. This is, I'm going to say that one of the cells. Okay, well, it is, copy is over there in other cell. One more cell, one more cell. And at the terminal parts, well, the cell is half. And here we have the supporting facility. You know, it is called abutment. Abutment. Yes, in this photograph, here is the abutment. Over there, there is a joint. The other abutment is over there. Okay. Yes, so well, at the part, the cell is half, you see. ending part, of course, cell half, but here cell is full. Cell is full. In this example, how many full cells we have in the structure of this truss? 1, 2, 3, 4, 5, 6 cells. Full cells and 2 ending cells. Okay, in my demonstration, I'm going to create the model of a truss. It will have 2 full cells and at the ends half cells. Okay. See how it is created. If you say that, hocam, okay, I open assembly environment and then one by one, after on a piece of paper, while using the trigonometry, considering the trigonometry of the truss, determine the inclination angle for each, and then determine the inclination angle for the ending surfaces of each of the members, and then edit them. Yes, using this technique, take a sketch, right, and then draw the profile and then apply cutting process, etc. And then can make the members with respect to each other, position them. I say that never select this way. Although there is a design wizard, like a magic, it is possible to create the main part of the structure even in few minutes. If you select the other technique and one by one have the models of each member and then try to position, I really say that you're in the wrong way. Don't select that way. Well, there is a method. It is the shortest way to follow, okay, in the analogy. It uses the design tool of Inventor. Well, if you're going to use the design tool of Inventor, where are the push buttons? Design tab. And I already addressed bolt, nut, or cap screw, threaded hole type joints. That is the wizard. And well, in the first project of the semester, assembly, yes, I educated you on the value of this design tool. Okay, talking about the pins, this week or next week, okay, latest maybe the time, I'm going to highlight the value of this design wizard. Okay, and then, well, this next week, I'm going to talk about this wizard, value of this wizard, and to the end of the semester, talk about the other design tools of Inventor. Along design ribbon, the listed buttons are just to make life easier for us. Magically, okay, can create the necessary thing at minimum period of time. One of them is just this facility. Actually, after reaching to this stage, you're going to see in few minutes how. Then this wizard will be just a panel. You see it is written frame. Truss is a frame. Okay. Structure in general. In the panel can have the push buttons as active after reaching a certain stage. Okay, insert frame is the first tool to click at the stage. After reaching to the stage, I'm going to make highlighting at the beginning of that stage, then clicked on this and then deal with the rest. So I address this facility along design ribbon, okay, using the tools of frame panel, can create the model of a structure such as a truss even in few minutes to its main part. Okay. Yes, now close this file, no need. Close this drawing file, and then truss. In this example, I said that going to demonstrate how the model of a truss can be created using the tool of Inventor. Well, the first stage in the procedure, well, the truss or whatever the structure is, it is to be schematically drawn. The lines, yes, for instance here, Warren type truss, similar to the ones, figures, those can be found in statics books, strength of materials books. Okay, it has been schematically shown. These schematically shown lines correspond each of them members, structural elements. But say at the first stage, saying that draw the necessary sketch, I mean draw the lines, okay, considering that line is passing through all the center points along all the cross sections throughout the member, throughout the element. Okay? And you know, already talked about it. To be able to prevent having bending moments, bending effects, the line of action of the forces, these are to be transmitted from one joint to the other joint. Okay? In other words, the forces exerted by the members at the joint are to be, are to pass through the same point. In other words, line of actions of the forces are to intersect at a single point. To be able to have the forces such that their line of actions intersect each other at a single point, yes, the force, it is acted by the member onto the joint. It is a resultant force, of course. Okay, is to be coincided with the line. It joins the centroids of the cross section of the member. How many cross sections can be defined along a structural member? Theoretical answer, infinite number of cross sections. Okay? If the resultant force, just to its line of action coinciding with the line, it joins the centroids of the cross sections of the member, yes, can say that when you position the member, okay, using the inclination angle of such a line, saying such a line, I mean it is the line which joins the centroids of the cross sections of the member, and then accordingly load the member, its line of action coincides with the line which joins the centroids of the cross sections, then can use the inclination angle of such a joining line as the orientation angle for the member. And then if you use the angles for each, then can guarantee to have the line of actions of the forces, okay, applied by the members intersecting each other at the same point. So, well, at the sketching stage, well, in using the design tool of Inventor, the first stage is sketching stage. In sketch mode, as the sketch, well, draw the lines and say that those lines are just the lines joining the centers of the cross sections of the members. Okay, draw this line, draw this line. These lines in schematic drawing corresponds to the lines, repeat again, which join the centroids of the members. Okay. Yes, now, after this little bit detailed explanation, during the application, you're going to see what I mean much more clearly. Okay, to be able to have the necessary sketch, click on New File Creation button. Okay, And then select the unit system. I'm going to use metric unit system, so I selected metric option here. And then, well, have the sketch in part environment. Do not say, yeah, hocam, it is an assembly. Yes, I know the structure is an assembly, but the sketch, it is just a line, group of lines to use following stage. Okay? Well, through the sketch, it is going to be just the lines corresponding to the ones which joins the cross sections of the members. Okay? In part creation environment. Select standard.ipt template and then click on create button. Yes. And then sketching stage. Clicked on 2D sketch button and select one of the coordinate planes, this or that, which one you like. It is my tradition. I select, I don't know why, but it is my convention, always the horizontal oriented one. How? Bring the cursor to the core part of the coordinate plane, and after seeing such a color changing, click the mouse. You know this. And in sketch mode, well, schematically draw the truss. In doing this, the lines, just consider that the ones they are passing through the centroids of the cross sections of the members. Well, there will be in this example 2 full cells. So, well, instead of drawing the schematic of the cell line by line, I know the boundaries form a rectangle, so I selected rectangle creation button to save time. Created a rectangle arbitrarily, and then snap this corner, create one more rectangle arbitrarily. Okay. First, size the full cells, dimensional constraint. Well, from here to there, the length of the cell, I'm going to say 2 meters, 2000, and then of course, after writing such a big number, the sketch is out of screen. Zoom out, call it, okay, and then continue. The height of this cell, let's say, is okay, then 1 meter, 1000. And then, well, use the same dimensions for the second cell. It is width is 2000 and the height is 1000. Yes. And then, well, diagonal direction for the stability of the truss. Yes, these are needed. Snap this corner, snap that corner. Okay. Continue. Snap this corner, snap the corner, other corner. Yes, you see symmetric 2 cells, this and that. And then ending cells. Repeat again. This line, for instance, if you wonder, yeah, hocam, what is that? Repeat again. Well, there will be a member following stage in model, at the model creation stage. Well, and that line will be the one passing through the centroids of the cross section of that member. Okay, these are in my consideration the lines which joins the centroids of the cross sections to each other, or passing through the centroids of the cross sections. Okay, start line drawing process, and then or create a rectangle, which one you want. I'm going to create and trim the half to have half of the cell, or line by line. Yes, I created a line and then one more line arbitrarily. Press escape button, restart. Do the same thing at the other end. Create a line, create one more line. Okay, and then correct the geometry. I'm going to make this boundary perpendicular to the other. Perpendicularity constraint or select horizontality constraint. This and that are perpendicular. Perfect. This and that are perpendicular. Yes, it's a right triangle. Okay. I'm trying to have such a thing. Yes, half cell. Yeah. Abutment, etc. And then size it. Well, the width of the half cell, say that 1000 try 1200, let's say. Of course, well, we select the lengths of the cells regarding the strength of the members and the maximum deflection of the bridge or truss, and of course the span of the truss. Well, if the river, okay, to have the bridge across the river is in the width of, in the span of, for instance, 10 meters, then the total length should be minimum 10 meters. Okay, from abutment to abutment, one side to other side. Okay, so not arbitrarily considering the span of the river or whatever it is, say sea, or I don't know, it is the structure of which one. If it is in the construction of the roof structure, then well, consider the maximum size of the roof to have, then accordingly decide how many cells you need to use. Okay, and it is the other issue. If the cell width of the cell, for instance, were greater than 2000, then well, under the action of gravity force, then the deflection of this member will be a little bit more. So, well, I don't want to have such a deflection order. So, select the length of the member in this order. And while you're taking strength of materials course, you're going to learn some other things. For instance, especially for the vertical members, well, determining the strength of the member, so correspondingly selecting the cross section in the necessary size. Well, we consider not the normal stress, but also say that for the vertically oriented members, the other important thing is the stability of the member. Okay, well, there may be unexpected deflections under the action of the vertical loading. Okay, so consider not only normal stress but also the stability of the member. Okay, cylindricity of the member is an issue. Later you're going to see, while you're taking strength of materials course, what is cylindricity, and then to be able to make it stable, what should be the minimum length, maximum length of the member. So considering the cylindricity of the members, say that I selected the maximum length for this member as 2000. Okay, but this member is 1200, let's say, in length. Okay, for this one, do the same thing, 1200. Okay. Saying the necessary sketch, I mean such a figure. Okay, then finish this sketching stage. And then save this file. After the sketching stage, normally we apply process, revolve, extrusion, etc. But no. In using the design tool of Inventor, it is for creating the models of structures. In part environment, do not apply any process. Just have the sketch. And then save it. In the memory, save as. Of course, it is going to be the project folder. Inventor knows that it is the active project. And then name this sketch. it is the skeleton corresponds to the schematics or skeleton. In the analogy, I may use those lines just passing through the centroids of the cross sections of each member. It is like our skeleton. Okay, so I'm going to use in the analogy this word. Okay, or if you want, say that sketch for truss 1. Okay, this may be more reasonable. Sketch for truss 1. Sketch of truss. Okay, sketch of truss. Good. Save this file. And then yes, close this file. No need to keep it open. And then for creating the model of the truss, in our example, the structure, the frame is a truss. Yes, open assembly template, new file, assembly, metric unit system, which template standard.iam in accordance with ISO. That is the, to have the things, that is the template option. Clicked on create button, and then call the skeleton, call the sketch of the truss. How? From this list, it is selecting place option. And then here is the file, sketch of truss, as if it were say solid model. Okay, just invoke it, indicate and say open. Yes, and then locate it arbitrarily with a click in the space. Well, since my demo is about only one truss, well, I'm going to use it one time. But to have the other truss, yes, it is a technique to the end of my demo. This, it may be just a following record. I may say that, okay, to be able to have the model of the bridge, not only one of its trusses, but the bridge, yes, use the truss, skeleton of the truss twice, this and that. But here I don't want to make a demo on such a thing. My purpose is to clearly explain how a truss can be created, the model of a truss. In general speaking, say that how the model of a structure can be created. Answer this question for a two-dimensional structure first. Truss is a two-dimensional, you know. So, well, I'm going to have only one skeleton to have only one truss, only one structure. Press escape button. And then when I open the file, I want to see the truss as oriented like this. Okay. So, well, you know, I'm going to define this positioning as the home positioning. Bring the cursor onto the home symbol, right click, and from the list, on the list it will drop. Bring the cursor onto set current view as home option, and then jump to here and select fit to screen option. And then whenever you clicked on cutter symbol, then you see the model, or here there is no model yet, the skeleton in that orientation. Okay, it is recommended. Yeah, well, if you, when you open a file, you want to see the model is oriented in which direction, then, well, decide and then define that positioning as the home positioning. And then, well, here I'm going to make a quick demo just to highlight the value of the design facility. It is like a magic. Although if you attempt to have the members as mated with respect to each other one by one, creating the model of such a truss, it is, a small truss, little truss. It has two cells, two complete cells only. Well, think about it. If the work were on such a truss, how many cells? Then try to have the models of the members at the joints correctly positioned one by one, cell by cell. Oh, it is a tedious work, would be. But here, using the design tool, can create the model. Not a matter there are two cells or n cells. The time to create the model of a truss, even for a very long truss, is in the order of few minutes using the facility. But using the facility, yes, can create the model of the main part of the model of the structure in few minutes, but there may be some mistakes on the orientation of the members. Okay. In this example, the members will be U-shaped members. The cross-section of the member is like letter U or letter C. Okay, and then, well, the orientation of such a member will be important, of course. Well, after creating the model of the truss, I'm going to explain what I mean. Okay, then first see the magic. Select Design tab, and then you see it is written Insert Frame. Or instead of saying Insert Frame, then it would be better, more understandable. Create a frame. Clicked on this button. Well, I forgot to save the file. Whenever you attempt to use the design tools for creating bolt joint, pin joint, or creating the model of a frame, or creating the model of a shaft or gears, etc., Inventor will bring this notice. Yes, first save the file and then continue. Okay, I'm going to save it. Yes, thanks to this reminding, I see that time to save. Okay, save this file. Previous meeting said that in the environment had only one member and set it assembly 1. Here in the order it is the second assembly, but instead of assembly 2, I'm going to say truss. Truss 1. If there will be a bridge, the model will be the model of a bridge, then there will be 2 trusses. Okay, so say that order the trusses. This is the assembly file. It is going to be sub-assembly by definition. Main assembly is the bridge. Sub-assembly is the truss, one of them. So according to write it is name. If you are a student in school, then, well, you know the request. Write your surname, etc. Okay, ID number, and then say the meaningful part of the file name. Write this word truss. Which truss? One of them, truss 1. Okay. And then yes. Remember, I saved the file and then clicked on this Insert Frame button, or clicked on this button and Inventor noticed me that first save the file. Okay, I save it, and then this is the following stage. This dialog box will appear in the screen. Well, introduce what we have in this dialog. Well, this part, it is a pane in the dialog box. Well, you see there are some radio buttons. And the radio button at the center has been selected. This one, no. That one is the selected radio button automatically. What is that? Consider this radio button as a point. It is just the centroid of the cross section of the member at one of the cross sections. And well, in our skeleton, for instance, this line, say, repeat again, is the line which passes through the centroids of the cross sections of the member. Yes, this line passing through the centers of the cross sections. So, well, this simulation, this circle is the cross section of the member. Well, automatically selected structural member is the one having a solid circular cross section. This point at the cross section, the center of the cross section, and sure, in the consideration, it is one of the points along this line, since the line passing to the centroids. Well, if you're going to consider this line not as the line passing to the centroids, but say that it is just at the place where the centers of the cross sections, okay, should be shifted to the right or to the left relative to this line. Okay, then select this radio button. After selecting this radio button, in this direction into this box, write the shifting value. It is to say that, well, creating the model of the element along this line, okay, well, do not bring the centroids onto the line, but say locate them as shifted. For instance, say that 10 millimeters, 100 millimeters, okay, in the horizontal direction to the right. If you select this one, in the horizontal direction to the left. If you select that one, then shifting into this box, it is to be written. Say that create the model of the member relative to this sketch as shifted. For instance, write it 20 millimeters in the up direction. Okay? Or select this one in the down direction. But if you select the center radio button, then the centroids of the cross sections of the member will coincide along the skeleton, along the line in the skeleton, in the sketch. Yes. First see, well, create the members such that their cross sections just along the already drafted sketch. So, well, this boxes the offset value write 0. You do not need to have a shifting in, no need to shift the member, okay, with respect to this skeleton. Okay. The other thing here, placement option, saying that it is the skeleton of the member. Shall you indicate the member with 1 click or 2 clicks? Well, this is advantageous. Instead of, if you select this one, then you need to indicate terminal points, both of the terminal points. But here I'm going to indicate the member except terminals at any other point. It is easier. Okay. I'm going to talk about this angle facility later. We use this facility to change the orientation of the, structural element with respect to the others, to have it in the correct orientation. I'm going to make the sentence clear enough. Following stage. And then this part of the dialog box, well, obvious standard, select the standard. You're going to have the structural members as the ones designed and manufactured in accordance with the rules of Which standardization association? That is the question. Drop the list and select the association. The abbreviation, it corresponds to that standardization association. Unless otherwise mentioned, use the ones manufactured in accordance with ISO. And then, well, the second list is to select the type of the cross section. Which kind of structural element you're going to use. Well, select a few of them and then see the changing. For instance, in the list, it is at the top. Select it with a click. Yes, it is the automatically selected option. This means the cross section of that structural element is circular. If I select the second one, see the changing. You see the cross section is rectangular and it is solid. Select the third one. See the cross section. Yeah, it is circular, but inside is empty. So annular cross section, like a tube. And also here there is a short explanation. Circular hollow section. Well, the next one, it is written rectangular structural steels, cold form welded. Okay, hollow section. Select this option. And then you see the cross section is rectangular, inside is empty. Okay. Try the others, you may. Select this one. It is an L-shape member. Cross section is L-shaped. Yes, the list is in this order. Well, select the others. For instance, halt rolled steel sloping flange channel section. Try to use this one. Yeah, yes. In my demo, I'm going to use this cross section. It is, you see, like letter C. If you change its orientation, rotating it 90 degrees, then it is going to be like letter U. Yes, it is the selected cross section. Of course, selecting the cross section, we consider center of moment of the cross section, strength of the member, and some other design aspects. But here in this example, I selected this cross section, not I-shaped cross section, but C-shaped cross section. And then the third list is the list to select the size of the cross section, shape of the cross section, and then the size of the cross section. In this example, say I know 80 is the height of the cross section and 8 is the average thickness of the solid parts at the cross section. Well, say that the height of the cross section, say 100. I selected this one, not arbitrarily, of course. I solved the design problem, and I know that to be able to make the members strong enough under the action of the forces acting at both of the terminals. Okay, if the size of the cross section becomes equal to that much, then it is going to be sufficiently strong. Okay, and also in this size, it is going to be stable. Cylindricity check also saying that, yeah, this is the correct size. While you're taking design course, strength of materials course, you're going to learn the necessary things and understand what I mean. Say that this size is determined by the designer. Okay. And then material, mild steel, it is standard material. Okay. And then the rest. After making such selections and deciding that cross section, that is the centroid of this cross section, and consider that the line joining the centers of each cross section coincided with this line. If yes, then select the central radio button, I said. Okay, and then my demo, just to highlight the value of structure creation tool. Well, to be able to prove that even for a very long truss, or in general speaking structure, time period needed to create the main part of the model is in the order of even seconds, just see my demo. Using windowing method, select all the lines corresponding to the skeleton of the truss and release the button. That is it. And then system, you see the simulation about to create. Just say OK. And then say OK. And then say OK. Yes. Magic. That's it. Finish. The model of the truss. You see, in order of minute, it is possible to create the model of the truss. And see the value. You see, mating is achieved by the software. No need to use this facility, face-to-face contact, inclined positioning, etc. Well, the orientations of the members are perfect. Okay? Correct. Because I said that locate the member, coincide the member to its center line onto the existing skeleton. So since I created the skeleton using the true angles, so while the created truss uses the same angles and the inclination orientation of the members are all correct. Okay. After making such a highlighting, then, well, focus your attention to some problems. Yes, Inventor created the model of the structure in few minutes, but when we make zoom in at the joint, can see that there are unrealistic things. What? This member interfered with the other member. In physical world, it is impossible. How we can have within a solid body another solid body? There is an interference here between this and that, between this and this, between this and that, and the others. It is a problem and it is to be solved, it is to be shot. And at this joint, yes, again, we have unrealistic interferences, this joint, etc. Well, editing is needed, and Inventor in design ribbon, along the design ribbon in frame panel, yes, after creating the model of the frame, then yes, not only insert frame button, but the others are all active. Okay, these are mainly the editing tools. Okay, well, to be able to make the joints not unrealistic but realistic, prevent such interferences, well, use the trimming facilities. Following stage, I'm going to demonstrate how. But here, my purpose here at this stage to draw the attention to another problem. Yes, creating the truss, well, my purpose is to orient the member like this. No, not like that. Like this one. Yes, the flat surface or the member is to be positioned horizontal and toward the surface of the earth. Yes, you see the cross section is in U shape, C shape, see the cross section. But here my purpose is to have the member as oriented like this. The positioning of this member is correct. It is flat surface is toward the surface of the earth. But the next member, you see, unfortunately, the orientation of next member is wrong. Not the C-shaped cross section, say that it looks like legs. Here in the correct position, the legs are in the up direction. Okay? But for this member, the orientation of the member is wrong. Okay? The flat surface is at the top. Legs have been oriented in the down direction. This is wrong. For the next one, orientation is correct. This one, orientation is wrong. Okay? Well, you see, Inventor magically created the model of the structure while orienting some of the members as I desired correctly, but the others wrongly. For instance, here, the orientation of this member at the top edge is correct. Flat surface, I want to have the flat surface as horizontal oriented and well, toward the up. Legs ought to be down direction. But for the next member, I cannot say the same thing. You see, the next member in its orientation, that characteristic, the legs are upwardly oriented. Yes. Similarly, can say that I don't want to have this inclined member as oriented like this. It would be correct if it were 180 degrees rotated. Okay. So, well, using that facility and using windowing method, selecting all, magically in few seconds even can create the model of the truss. But the orientation of the members may be wrong. Some of them may be as you desired in correct orientation, the others wrongly oriented. So, after making such a impressive demo to say that, yeah, it is like a magic, then I'm going to say, oops, undo. And then talk about the method, okay, how you can have the members as correctly oriented, the oriented as you desired or as you selected. Answer this question. It will take, of course, a greater time, but say all the things going to be under your control. So at this stage you can check whether the orientation of the element is correct or wrong. Okay, restart. I invoke the skeleton, the necessary sketch, and then, well, save the file and then clicked on Design tab, and along the ribbon, well, frame creation facility is in this panel. Okay, and the first button to click, it is for structural creation purpose, is insert frame button. After clicking on the button, then yes, the same dialog box. I decided to have the centroid of the cross section along the skeleton, along the lines of the skeleton. So I selected the central radio button. Okay, standard is ISO. The type of the cross section is this one. From this list, I selected this one. Okay, and then from this list, I selected the size of the cross section. And then material is standard, still mild, and then the rest. Instead of using windowing technique, selecting all, select them one by one. I'm going to start from here and then make zoom in, make a click. And then check, see the simulation. In the simulation, I see that the legs are in the up direction. And the flat surface, flat outer surface is in the down positioning. It is just toward the surface of the earth. This orientation is the correct orientation. And then clicked on apply button. Well, and then say OK. And then one more time say OK. Yes, I accepted this member. And then I think you get it. And then indicate the next one. and then check from the simulation whether orientation is correct. It is correct. If it were wrong, now see the usage of this one. I will rotate it. For instance, see how it is rotated. Whenever the legs are in the wrong direction, then, well, rotate. How many degrees? I know that if I rotate it 180 degrees, I can change, upset it down. Okay, now you see its orientation is different. Okay, 180 degrees rotated. But of course, it is the wrong positioning. I'm going to select 0 degree. Yes, that is the function of this facility. Whenever the orientation of the member is wrong, and say see from the simulation whether it is to be rotated 180 degrees to orient it correctly or 90 degrees, then accordingly in which direction, clockwise direction, counterclockwise direction, select the angle options. And then, well, if you say that, ya hocam, clicking on for each apply button and then OK button and then continue on the rest is too long, then you may take a risk. What is the risk? You may indicate not only one but 2 or more and then say apply, but you may see the one of them in the wrong orientation. What can you do? Say oops and then do it again. I don't want to take such a risk, so well, one by one continue on indicating them. This one, yes, correct. Or I said that I don't want to take a risk, but say take a risk, yeah. Try this one. Yeah, it is great. I am lucky. The orientation is correct. But I don't want to take a risk for the other. So say after having the simulation for 2 successive members and seeing that these are in correct orientation, I don't want to take the risk one more time or furtherly. Clicked on apply button and then say OK and then continue. Well, indicate this part of the sketch to say that to this line fit the member and then check whether orientation, yes, the legs are in the correct direction. So, well, apply and then say OK and then continue. This one indicate and then check whether the legs are in the down. No, it is in the up direction. So the orientation of this one is wrong. Need to rotate it. I know. Upset down 180 degrees. And then check carefully. Yes, the legs are in the down direction. Along the bottom edge, up direction. Along the upper edge, down direction. And then clicked on apply. Say OK. Continue, indicate this one. And then check the legs. No, unfortunately, legs are wrong. So rotate it. Well, in that case, since well, I said 180, I found it just wrongly oriented. So I know I should say select 0 degrees. Okay, and now it is in the correct orientation. I don't want to take a risk for the next, say apply. You see, it is not so time consuming. 2 extra clicks are needed if you don't want to take risk for each. Apply and OK. And then continue, indicate this one. And then check whether the legs are in the correct direction. I couldn't understand. Did a bit rotate the model. Yeah, yes, I see from the simulation the flat surface is toward the outside. So this orientation is correct. Apply. Okay. Yeah, mating. You see, the most valuable part of this facility is mating. You see, just simply indicating the skeleton and the orientation, not the cross section but the member with respect to the others at the joint, just achieved by the software. Okay, and then continue. Indicate this diagonal member, or this one. Which one? Okay, indicate this one. And then yes, okay, well, for the vertical one, not a matter, it is legs are to the right or to the left, it is okay for me. But say this is important, if I found the member as rotated 90 degrees, then I would change it as orientation. Okay, I can indicate the other vertical ones. Okay, it is okay. Well, the orientation of this one is okay as well. Then click on apply button and then say okay. Yes, and then the diagonally oriented ones, indicate this one. And then from the simulation, I want to have the flat surface as oriented to the up direction, in the up direction. I see from this simulation, legs are inclined but toward the surface of the earth, so this orientation is better for me. So clicked on apply button and then say okay, and then indicate the last part of the sketch, and then see the simulation. Well, this member, I see from the simulation, the legs are not toward the down but up direction. So I'm going to rotate this member before saying apply 180 degrees. And now it is, flat surface is in the up direction. Okay, and then say apply, then say okay. And then that's it. Yes, well, the truss is ready to its main part. And for all the members, since I selected their orientation under my control, just using the orientation angle here if necessary, I'm sure as I desire to have them, they are in the correct orientation. So I finished the main part of the structure creation process. Okay, I had the model, clicked on this button to shoot this dialog box, and then, well, time to save it one more time, clicked on save button. And then, well, I added lots of things. Inventor saying that, do you want to save changes? Yes to all, and then say okay. Yes, at the background, lots of data files created, and in which Inventor will keep the geometrical relationships and also the characteristics of the members, which kind of member I selected, the length of which one is equal to how much. These are all recorded. And then, well, the interferences. Okay, it is unrealistic, of course. Well, before ending this video record, well, only for 3 joints, I'm going to demonstrate what is the thing to do for preventing such an unrealistic interference. In real world, impossible to have at the joint 2 members interfered with each other. In physical world, impossible. And well, of course, say here, for this member, the terminal parts are to be trimmed. Inclined edges are to be created. Okay? Well, select this one and edit. No, well, it is not so easy because, well, need to calculate the angle and also the size of the part to be able to prevent angle of the end of the member to cut it accordingly, and also what is the size of the part which is in interference. I don't want to answer these questions, actually no need, because well, we have in the structure of the software within frame panel all the necessary editing tools. If it is just the joint where you have two members at the joint, then yes, apply this process, metering. Meter. Okay? It is the tool to prevent having interferences at the joint. Which kind of joint? The joint, well, over there we have the meeting of two members only. Okay. Well, this joint, yes, I have two members. So click on metering button and start the editing process. Yes, that is the dialog box. In the dialog box, yes, there is a schematic drawing in this pane. One of them is one of the members, the other is corresponds to the other member, and well, metering them at the joint, well, whether you're going to have between the edges of those after trimming, after chopping stage, whether you're going to have a space. Well, if you're going to apply welding process, not fillet joint but boot joint, you're going to weld this member to the other using boot joint method, boot joint, both type joint. Then yes, to be able to position the electrode, okay, to here, between the edges of the members at the joint, there should be a space. Regarding the diameter of the electrode and the necessary allowance to swing the electrode, what should be the space between them? Okay? But if you say that, no, well, I'm going to connect the members not directly to each other, but using gusset plates connect them to each other, then yes, well, this space may be even 0. Didn't decide right now. Well, here I'm going to say that, okay, there should be between them how many? Make a click here, say that 5 millimeters. Empty space. I decided. And then the rest. Indicate the members. Order is not so important. First this and then the other, or vice versa. That is it. Then Inventor at the background, well, if necessary, will extend the member or members, but in doing this, trim the portions, otherwise they would interfere. And just click on apply button if there is only one corner to meter, or if it is, say, if you have not only one corner to meter but more, click on apply. But if there is only one corner to meter, then click on OK. I have not only this, but at the other end I have one more corner, so I'm going to say apply and then see, okay, the magic. After clicking on apply, zoom in, you see, well, here at the corner I see that members furtherly extended, but their interface portions deleted. And between them, between the ends of the members, as I fixed over here, there is a 5 millimeters empty space. Yes. I shut the trouble at the joint. There is no interference. Okay. And then do similar things here at this joint. Indicate this member, indicate the other member. That is it. And then say apply. But since there is no more joint having two members only, I'm going to say OK. Yes. This end, this joint, there is no interference. Save the file one more time. Yes to all. At the background, Inventor created some other data files to keep this info. And then, well, I'm going to prevent this interference. Using trim extent, trim to frame, which one? Call my memory, trim to frame maybe. No, not this one. My favorite tool is this one, trim extent. Yeah, yes. Okay, for the joints, well, you have more than two interfared members. My favorite tool for editing to prevent unrealistic interferences is trim extent tool. And then, similarly, if you're going to need to have space to allow the welder to position the electrode between them, a certain empty space is needed, then into this box write. In this exercise, say that 5 mm space is sufficient. Or depending on the size of the point of the electrode, well, see the diameter of the electrode and then minimum write the diameter of the electrode into this box. 5, let's say. And then, to be able to indicate what I am doing, I tilted it and allow myself to see the things three-dimensionally. And then see, blue, yellowish. Well, blue corresponds to the member, it has an interference. Yellowish corresponds to the target, a surface. It is to say that after that surface, chop the rest. You see, after this flat surface of this vertical member, I have an interference. The rest of this member, after this limit, is interfering. So, well, first, this button is on. It is to indicate the frame member. It is interfering. Indicate this one. I know that it is interfering. And then select phase indication button and indicate in this schematic view the yellowish one. It is this surface. This is to say that after this surface, chop the rest. Indicate this one. Inventor in the analogy, just after your indications, well, use the same colors. You see, the first indicated one is blue. The indicated surface is yellowish. Yes. See the simulation, and then if you say that, yeah, yes, these are correct, which member is to be trimmed, then OK, apply button. Clicked on apply. And then see the magic. You see the interfered part of this member in this direction. Have a look at. Chopped by the software. And between them, you see there is no interference. And between the ending surfaces, ending surface of this and the side surface of the other, as I fixed, 5 mm empty space. OK. Good. Continue. And then, here, this side. Shall you trim the end of this or end of the other? Because they are interfering. Decide which one. Okay, I'm going to trim the end of this one. So indicate this one, clicked on phase indication button, and it is to say that after this surface, I have an interference, to this surface chop it. But here, if I chop it, then here it is going to be necessary to indicate this one more time and that one as a target. So instead of saying that up to this surface, after this surface, then chop the rest, I'm going to say that to be able to prevent the interference in both of the directions, indicate this surface. It is, you see, the flat surface of the leg. It is the limiting surface. Zoom in, and then be able to indicate that it is not a curved surface. So flat, it is a curved surface. It had to be flat surface. Indicate the correct surface. I made a mistake. It is not the surface. It is the flat surface of the leg. It is over here. I indicated it. But since I made a wrong click, I should say cancel and do it again. Start the trim extend process, indicate this member, and then clicked on phase indication button, and then zoom in. I think this is now correct, the flat surface. Yes, it is the limiting surface of this member, and then say apply. Yes, you see, zoom in, the interfered part of this member chopped by the software. Following video record, there will be a gusset plate over here, and at the opposite side, other side as well. I'm going to talk about the gusset plates next video record. Okay. Well, here at this end, this joint, of course, there are some other joints. I don't want to repeat the similar things again. Okay, well, if you want, I may demonstrate how this joint can be edited, or how this one. I think this is more complex. Well, okay, talk about this joint. This is my favorite trimming facility, trim extend. And then yes, this joint prevent the interference. This is the member. It is interfering with this one. Okay. Well, rotate it and indicate the target surface to say that after this surface, trim the extended part of the first indicated member. Clicked on phase indication button and indicate this limiting surface of the other member. And then see the magic. If I say apply, then yes, between this and that there will be no interference. But between this and that there is an interference. You see, this part is interfering. So to say that, chop this interfered portion as well. It is not the part interfering this, but the other. So one more time indicate this and the surface of the other. Clicked on face indication button and indicate the surface. This is the limiting surface. After this surface, I have an interference. So to say that, chop the part, okay, of the member. It is beyond this limit, and then say apply. Yes, have a look at in the direction, and you see for this member at the joint there is no interference. Yes, continue. Indicate this member. I know it is interfering, and as the surface, indicate the surface of this or surface of the other. Zoom in, and then clicked on surface indication button, and then indicate the flat surface of the member, and then say apply. Yes. Well, prevented the interfering with respect to this. Since this and that are in alignment, you see I also, thanks to that chopping, prevented having interference between this and the other member. Okay, for this one, do similar things. Indicate this member with a click, and then, well, after which surface it is to be trimmed. Well, zoom in, indicate the surface, clicked on surface indication button, and then this is the flat surface of the member. After this surface, the rest is to be trimmed. Clicked on apply button. And then have a look at I have which one. Yes, for this member, with respect to this and that, I solved the interference problem. But you see this part of the member still interfering with the vertically oriented one. So I indicated one more time. And then clicked on phase indication button. And then, yes, indicate the boundary surface to say that after this surface, the rest is to be chopped. Zoom in, and then see this flat surface of the leg, tip surface of the leg of the member, and then clicked on apply. Yes. And then, well, these are just touching to each other, but I want to have between the end of this and the end of the other 5 millimeters empty space. Although they are not interfering, but using the trim extent facility of the software, I can have an empty space between them. Indicate this one as if interfering with a click. Clicked on phase indication button, and then, yes, when you bring the cursor to the end of this one, it is cross section will be highlighted. Yes, this cross section. Okay. Between this and that, there should be 5 millimeters. Then say apply. Yes, you see, managed to have a space. It is for welding to insert the electrode. It is, let's say, necessary. Yes. And then for the other joints, patiently do similar things. Okay? But here, since there is no new thing to educate you on the same thing, well, I'm going to say that assume I edited the other joints as well. Okay? Do not make the size of this video record too much, repeating the same thing. So, well, good practice. I use the skeleton. Okay, you know how and why. And then I want to take it as visibility from the domain. It is not a good thing to see the skeleton with the associated constraints. Well, find the icon, skeleton truss, clicked on this cross, and then here is the sketch icon, right click the mouse, and the select visibility option. Yes. Save the truss one more time. And then, well, by the next record, video record, let me say that, my dear students, bye-bye, have a break. After the break, I'm going to talk about gusset plates. Okay? At one of the joints, demonstrate the things to do, how the members can be connected to each other. In answering this question, I'm going to use welded joints. I'm going to connect the gusset plates to the members at the joints, applying welding process. And also answer the question how the gusset plates can be created and positioned. Next record, it is going to be the subject. Yes. See the answer of such questions after the break. Bye-bye.